So welcome to today's session, participants. And today we have Boldizsár from Continuum, who is also a researcher at Oxford. So he will take us through today's session, which has to do with measurement and no quantum copy. Again, welcome, Boldizsár, to this program, and we hope that you will have a lively session. Thank you.
Yes. So my name is Boldizsár. Thank you for this invitation. And today I am going to be talking about measurement and no quantum copy. The previous lecture, you guys have been exploring these spiders. And in particular, something that is going to be in focus today are these preparations. So these are, if I am correct, this here is a classical wire. And when you have two wires coming out, that corresponds to a quantum wire or quantum information. And similarly, we have measurements. In this case, what you would be doing is not prepare a classical bit in some quantum state, but rather have a quantum state, and then you kind of somehow measure it. And then I'm not sure how much you have discussed it, but you have two basis states in which you can measure. And there is something I believe you have not seen yet, which is kind of this alternative measurement. So this is quite interesting, right? Because what you have is we have a quantum wire here, and then actually the output is also a quantum wire as well as a classical wire. And then you can kind of think about how would you be able to implement this. And if you remember correctly, we had a rule called fusion that you can use to even unfuse spiders. So in this case, this was a fusion rule, right? You could fuse it back. And this is completely fine. So what we did is we had some quantum information. You might know that this can't be copied, but what we did is we first measured it. We first measured it, giving us a classical bit here. And then we can, of course, duplicate that classical bit, and then we can encode a quantum bit again, according to our measurement outcome. And then a question then might arise, what happens if you kind of try to do this alternating measurements by saving your qubits one after the other? And again, you should be familiar by now with the rule called leg chopping. So what will happen is all of these will disconnect. And then again, something quite remarkable is that here we measure something and then we get out the classical output. In the middle, sorry, I am not used to use, okay, doesn't matter. In the middle, you will have some random noise, and then again, some random noise at the top. And another interesting thing is that here you have measured something, right? You get a bit outcome. And then you do all these other measurements, you will have some random output, nothing related to what you have inputted here. So this is kind of the picture in terms of spiders. Something else which is worth kind of remarking is you could do something called a post-selection. So in this case, what you have is you have done this measurement, and then you kind of post-selected on your 0 bit, right? So this you probably also have seen this corresponds to cat0 or bra0 in this case, because it's a measurement. And we can also see that in the ZX calculus, we can kind of separate these legs first, and then we can copy this basis state or this spider into the rest of the spiders, and then we can kind of make it again a quantumly thing, giving you kind of this post-selection bit, as well as what you will get as an outcome is going to be this zero state, and it's kind of going to eat away anything else that's not related to the zero state. And I thought it would be quite nice to kind of tell you a bit more about how this would look like in an actual experiment. So this is a very famous experiment done by Stern and Gerlach in the 1920s. So what they did is they have a kind of a gun, which you can think about it kind of shoots out qubits. And then here they have two magnets, or a magnetic field. One of them is north, other one is kind of south. And what happens if you shoot out a qubit? Would it go kind of like a line here? It turns out no. So what happens is it either goes up or it either goes down, but it's never going to be in between here. And it's quite remarkable because at this point, your qubit could have been anywhere in between. So the way you think about it is these block spheres. So your qubit could have been anywhere on the ball sphere, but once you enter this magnetic field, it is going to change its state. And at this point, I'm going to just draw it here. It's going to either flip to the top or flip to the bottom. So depending on kind of where you were, with certain probability, you either get something which points up and then it's going to go up, or something that points down and it's going to be going down. So this is Stern-Gerlach. And this is how I would relate to you this measurement spider, right? So what did we have? We have some kind of quantum state at this point, and then in a way we have interacted with this quantum state, and now we have a measurement outcome, right? So we see either it went up, which was the cat0, or it went down, which is cat1, and this corresponds to a classical bit information. Then, so this was, the previous one was the green spider, but we could do the same in another basis. So this bulk sphere I have drawn to you before was kind of a three-dimensional sphere. And it turns out you could do three kind of measurements in each plane, but we are right now going to focus on X and Z, so the two spiders. And in this case, we could do another kind of measurement, which would be corresponding to a red kind of measurement. So here, our spider is going to be red. And this corresponds to, in this case, when your magnets are kind of placed in this horizontal plane. And then what happens if you kind of don't measure after having made your qubits or your particles go these two ways, but rather you put some bigger magnets and you kind of again put them onto the same path? Then what you kind of did is you have had a quantum state, and then you have made it kind of collapse into one of this elementary basis states, computational basis states, and then you put them back together. And then you could represent it as the following spider, right? So what you have done is you have kind of measured it. So in this case, you don't have a classical bit information. You kind of forgot about that. But you could think about this in such a way. And then you made a new spider, a new quantum spider. Again, this was something we had seen before. So then one of the interesting questions is, can we kind of stack these things? So first, could we do a Z and then an X measurement? And of course we could. So we make our particles kind of collapse in different planes. And this corresponds to this kind of spider, right? So first you measure in your green basis or Z basis, and then you do it in the X basis. And again, this is going to disconnect these spiders. This is a very nice way to see these results. And then again, an interesting bit is that because of this leg chop, this is going to be a random state at this point. And here so the first one was the real measurement, and afterwards you kind of just get random outcomes. And so another interesting thing is post-selection. So this would be post-selection. This is how you can think about post-selection. So with this, you kind of ensure that your basis state is only going to be cat 0. So let me just get this printed out, and then I can show you it in terms of spiders. So yes, this corresponds to having kind of a cat 0 here. And we have seen it before. This is going to copy through. And then we do a measurement in the X basis. So that's this one. And then what we should try to do is, again, kind of put your particles back into one root, and then measure again in the Z basis. So in the classical case, what you would kind of want, or what you would kind of expect, is once you know that your particle was measured as a 0, then you do this other measurement. Here, you would also probably expect that it's going to be 0, right? So you know that your particle was in this cat 0 state. Then if you measure it again and again, you should expect it to be 0 again, but it turns out no. And the reason is it's because if you at this, so if instead of this X you measure it in Z, then yes, you would get the 0. But this X measurement, by kind of trying to measure or collapse your qubit, you have changed the way your qubit is. So again, it's nice to think about it in this bulk sphere way. So here you have kind of collapsed your qubit to be this up going vector. In this case, you have collapsed it to look one of the ways again. And then if you come here, this is going to be a 50-50 chance of either of them happening. So now again, looking up can happen as well as looking down can happen with 50-50 probability. Is this clear? I think this is a good place to stop for a second. Okay, I'll assume that it is. So let's go further, and this is going to be a very interesting topic again. So when you hear about quantum computing, there are a couple of things you hear that it's really good at. You know that it's kind of very powerful and very quick in certain applications, which is in a sense true. Okay, good. I see in the message. Oh, sorry, I haven't been looking at the messages, but now I see someone responded. Thank you. So what you know is that there are some algorithms that are very quick in solving very specific problems, and these problems are usually really complicated on a classical computer. Another thing you may know about is that these quantum computers are really good at securely communicating. So what you can do is you can do this protocol called quantum key distribution. And with quantum key distribution, you can create these encryption keys. And the brilliant bit about it is that it is provably secure, so it is impossible to eavesdrop this. And this is what we are going to be looking at in this part of the presentation. So first, just kind of to put it into perspective again. So let's assume that we have Alice, and Alice as well as Bob. And then Alice would like to send a message to Bob. So this is kind of our problem. And this would be fine, but Alice wants this message not to be read by anyone else. However, we also have Eve, and Eve is really, really keen to eavesdrop on the message. She wants to read the message and know what kind of communication is happening between Alice and Bob. And if Alice and Bob has only classical computers, they are going to be in trouble, and they will need to get access to some complicated encryption algorithms. But if they have access to quantum computers instead, what they can do is they can send each other quantum bits, and they can be absolutely sure if Eve was trying to eavesdrop on them or not. And if she was, then they know that this line is not secure, and they should not be communicating with this encryption key that they have came up with. So this is not going to be possible if they have quantum computers. So yes. So let's look at this in terms of our spiders. It's going to be a simple 4 steps process. So first, we have Alice. Now it's A. And Alice picks some random bit and then encodes it in a random basis. So she either chooses to encode it in this green basis or in this red basis, so Z or X basis. Step 2, Bob randomly chooses to do a measurement in either of the bases. And then step 3, Alice and Bob are going to broadcast their choices. And here there are 50, like there are kind of 2 possibilities, 4, but if you look at it in another way, there are 2 possibilities, and both of them have 50% probability. So they either chose the same basis state, in which case the bit, in which case the bit that Alice is trying to send to Bob is just going to go through. So this equals just this single bit going to Bob. So this is clear. Or, and this is where I should undo the writing, or they have chosen different basis states. So here I kind of only drew one of them because the other one is going to be the same. So what happens is the legs get chopped off, or they drop. This is the hop flow. I'm not sure you have heard this name, right? And then Alice might have tried to send some kind of bit information, but Bob is going to get random outcomes out of this. And since they broadcast their basis choices, they know if some of them, they know when this same choice was happening. So this is the important bit. They know, because of the broadcasting, when they have chosen the right kind of basis states. And in this case, the bit that Alice tried to send to Bob should be the same. Okay. So maybe something else I should mention quickly. Oh, damn it. Something else I should mention quickly is, so they know the bits that they know the times when they have chosen their bases the same way, and then they have a set of bits which they can build a public key, a private key with. So they have shared this key with each other. But what happens if Eve in the meantime, tries to eavesdrop, so tries to understand what kind of key they, or what are they talking about. So do you remember that these are quantum bits? And the only kind of measurement Eve can do is either a measurement in the Z or a measurement in the X basis. So this is what we have seen before this. Okay, I have messed it up again. So this, remember, this corresponds to just measuring it and then duplicating the bit, or copying the bit and then encoding again. So Eve have destroyed the quantum information. So then here, again, there are two possibilities. Eve is either correct or Eve is incorrect. So if Eve was correct, then we are in trouble because Eve has access to the same bit Alice and Bob does. And this has a 50% probability. But at the same time, Eve can very well be just simply wrong. And here, what we are focusing on is the case where Alice and Bob chose the same bits, the same bases. So in this case, what happens is that the legs, fall off, or they get disconnected, and both Eve as well as Bob get some random noise. So if Eve was eavesdropping, but Alice and Bob were communicating with the same basis state, they should get the same bit, but Bob now has a probability that he gets something random out of it. So this is not necessarily going to match with what Alice tried to send Bob. So they compare a random selection of their private bits, and then if there is way too much noise, so this is quite easily describable how much noise you can accept based on the noise that your qubit may have. So if you see that there is too much noise, then you can be sure that there was an eavesdropper and you should drop whatever you were communicating with Alice and Bob. And yes, so this is called the BB484 protocol, and B for Bennett, and another B for Brassard. So this is the famous quantum key distribution. So I hope this was clear. Again, I think this is the right time to maybe ask a couple of questions if you have anything that you may not have gotten.
Hello, Boldizsár.
Sorry?
Hello?
Yes?
Yes, I have a question.
Yes.
So does that mean that in a situation where the information was distracted by Eve, meaning that Bob is not receiving the real information Alice is sending, right?
Sorry, can you repeat that? So
what I'm saying is that I think Eve distracted the information that was sent by Alice to Bob.
Yes.
So I'm saying that means the information Alice is sending to Bob, what Bob is receiving is not the same thing as Alice is sending. So Bob received information in the form of noise.
Yes, exactly. No, absolutely. That's absolutely correct. Yes. So
okay.
That's very good to kind of reiterate again. This is the picture that is kind of trying to tell us that. So let's say, oh, damn it. Let's say, it's actually good that you wrote it out, that Alice encodes, well, this is kind of the zero state. So either bit 0 or bit 1, so false or whatever you think. So if Eve was not eavesdropping, then we know that Bob should be receiving cat 0, the 0 state, right? But in this case, Eve was eavesdropping and she measured in the wrong basis state. So Bob is going to get exactly random noise. So this has half a probability of getting actually cat 0, but it also has half probability that it's going to be cat 1.
Okay, thank you so much.
Of course, yeah, very good question. You mentioned something about Eve accessing the information either on the Z or X axis. Can you explain that again? Of course. So, what we are focusing on now is, oh no, I should do this. So what we are focusing now on is this case here. So we assume that Alice and Bob have chosen the same basis. So this should be the identity information that Alice sent should arrive to Bob. So this is clear. And now, so this is a quantum bit, right? This is a qubit. So what Eve can do with a qubit is she can try to measure it. If you have access to a qubit, right, you can only kind of do operations on it, or you can try to measure. And here, you have access to this bit, and you will have to measure it in some way, but you have two choices. You either measure it in the Z basis, which would be the green, or you do it in the X basis, right? So this is again similar to the picture we have seen before, where we had these magnets kind of in different orientation. Right, so if you have some kind of qubit coming in, you will have to kind of choose a basis in which you measure. And then here, it's going to be the problem for Eve that she can't know for sure the basis state Alice and Bob chose. Does that make sense? Good, oh, very good. I'm glad. Yeah, this is also very important. I guess we can wait a bit more for any other question. Maybe someone has. But if not, I'm going to finish this part on quantum key distribution. So kind of the takeaway is that if Alice and Bob has access to these quantum bits, they encode in random basis. So that was step one. Bob measures in random basis, step two. Then they broadcast what they got. If things don't seem to add up properly, then there was probably, with very high probability, so arbitrarily close probability to 1, there was an eavesdropper. Okay. So, so the next part that we are going to talk about is copying. If you have encountered quantum computing, there is this very famous theorem that you can't copy arbitrary quantum information. And it's a very powerful result, because this is what allows us to be sure that Eve cannot copy the information that Alice was trying to send to Bob. But on the other hand, it's actually quite annoying sometimes. So if you try to do error correction in classical bits, often what you do is you kind of replicate your information a couple of times. So that would be, you have something, you copy it, and then you just send this thing 3 times, right? And then if one of them went wrong, it's not a problem, because there are 2 other copies of it. So you're kind of sure, or with higher probability, your information is going to be arriving. But you can't actually do this in quantum computing. You cannot just arbitrarily try to copy everything. Sometimes it's quite annoying, but again, sometimes this is very helpful, for example, here. So let's try to prove it using these spiders, or more like boxes, that this is impossible. So we are going to define this box, this copy box. So let's try to stay with this eavesdropping case. So Eve had this bit, and then what Eve would have had to do is kind of copy this thing to herself and then send it off to Bob. So just a friendly reminder, this is a classical case, because in the quantum case it would be double. But first let's look at the classical case. So let's assume that this is the classical communication bit. So how do we want such a copy box to behave? If you remember from previous lectures, we defined this discarding box, sure box, I mean, you might be calling it. I'm probably going to be just referring to it as discarding. So what this discarding does is just whatever you gave it, it's going to forget about it. So if Eve copied this information and then forgot about it, it should kind of just be the identity towards Bob, right? So whatever Eve had, she dropped, and then Bob is just going to receive the information that he should be receiving. And it should go the other way around, right? So if Bob were to discard the information that he got, then Eve should just have this identity, right? Because you copied it and then you kind of got rid of it. So this is fine. So this is how it should behave in the classical, or even in the quantum case. And yes, this is exactly what I'm saying here. In the quantum case, let's say we come up with this magical quantum copy box here, right? What this should be doing is that if you discard information on one of its wires, oh, sorry, yes? I heard someone speaking. If you have any questions, just, okay, then I'm going to go further. So we have this quantum copy box. We had some arbitrary quantum information here, and it got copied to 2. If you discard it, then you should just get the identity wire onto the other side, right? And this should be the case for both of the sides. I think this is quite clear, right? This is very simple. And then you might be saying, like, we have seen in the classical case that we already have these spiders, and don't they just already copy? This was one of the rules I believe you have seen, right? So this was the classical case. Could we not just kind of double everything and then get this quantum spider? Wouldn't it copy? Well, indeed, it does copy encoded bits. So remember, this 108 is kind of cat 1, and this 0 corresponds to cat 0. So in this case, this copies cat 0, and then this one copies cat 1's. Right? This is fine. However, this spider cannot copy arbitrary quantum state. This is the important. If you have no knowledge of the state you are trying to copy, it can't do it. Just as a very simple example, we have this state. This corresponds to cat plus. And I am not sure you guys have seen it, so I'm just going to define it as the superposition of cat 0 and cat 1. And some normalization factor. So this is cat plus. If you input this into this spider, then this is going to fuse in, right? And then you can get rid of this spider here because it just has no parameter and then 2 outputs or 2 legs. So this corresponds to the cup in this maximally entangled state. Right. So what we wanted to do, coming back, is to copy plus, but then in the end we didn't copy plus. We created something totally different than plus. This is something very entangled. And in fact, if you remember, let's try to find this again. We had these 2 equations, right? We wanted our copy box to, this is all we wanted our copy box to do. If we discard either of the outputs, it should just act as the identity. And it turns out that our spider that we are trying to look at right now doesn't even satisfy either of those equations, because if you discard one of the legs, so this thing corresponds to just the cap, but it's interesting because it's kind of the two wires of the quantum get merged, so this is a trace. So they get connected, and then what you can do is just fuse them. And then you get this spider, and obviously this does not equal the identity. So this was nice, but why am I sure that, given the fact that this spider doesn't do what we wanted it to do, how can we be sure that there is no quantum copy? So the reason to that is going to be it's again going to be quite simple, but we are not going to be using spiders because what if there is some other kind of composition of these things that would, in some miraculous way, just act as the copy box? But first, so let's look at the classical case. So what we have is we have this hard box, and what we did is we kind of flipped it. So this is a transposition or adjoint. And then what we say is, let's make sure that this thing gets separated. So what this is some arbitrary state. Let's make sure that this hard box is defined in such a way that if you do this, then you get separated. So it turns out that this equation alone implies that the hard box was actually originally separated on its own. So again, let's kind of make it a bit more concrete. So here, this was the previous equation. Let's assume that these hard boxes, if you put them here, then they get separated. And in fact, the state that you see here, sorry, the measurement you see here is going to be the same as the state you see here. And the number 2 was what we said, or what I was trying to claim, is that if that one implies, sorry, that number 1 implies number 2 and the other way around. So why? Here, by number 2, this gets separated, right? So this is just kind of replacing each of the hard boxes with the value that corresponds to according to number 2. And then this is just a preparation and measurement. This corresponds to nothing. And then this is number 1, right? So this is 2 diamonds. Oh, sorry, this is, this is not there, but this corresponds to equation number 1 if you look at where we came from and where we ended up at. So this is quite similar in the quantum case. So if we have some kind of quantum box such that if you discard one of its outputs, it corresponds to something on a single wire, then it implies that the original box was actually disconnected from the part where this qubit was going, right? So this is what I'm trying to say. If we look at it in terms of this doubled picture, what this would mean is that we have this hard state, but this is now a quantum box. So we double everything. Has 2 wires coming out, 2 wires here and 2 wires here, and we discarded one of its outputs. So this, if we kind of expand the definition of this So what we were looking at is if there exists a quantum copy, and then we had these two equations that we wanted this quantum copy to satisfy. So if you discard either of the outputs, you should just get the identity wire on the other wire and the input. And then here, what I'm trying to tell you is that this was one of these original equations, right? If you expand this quantum definition of the Q copy, and this is how it looks like in terms of just single wires. And then from the previous derivations, this implies that this quantum copy is actually already disconnected, right? Because otherwise this would not be possible that this gets you the identity. And again, this implies that the quantum copy is already disconnected, which is a contradiction because it's then not going to copy. So what this is saying, if it satisfies this discarding for one of its wires, it is definitely not going to satisfy it for the other wire. So in this case, Eve and Bob. So in this case, Bob just discarded it and Eve gets some garbage, right? So Eve doesn't get any kind of useful information out of it. But then there are two of these equations, and if you put the two together, what you get that there is no quantum copy box that can be satisfied. So this is this no-go theorem that there cannot exist a quantum copy. And so this is the end of the presentation. This is what we should be covering today. We have about 10 minutes. I think this is a very good time for you to ask any kind of questions, either about a quantum copy or anything else.
Okay, hello.
Hey.
Please, with your title, like there were some place we're talking about the BB84 quantum key distribution.
Yes.
Yeah. So I'm asking, is it already is it applicable, or maybe it's just a theory? Maybe it's not applied anywhere yet.
This is actually a very good question. So I am not sure how applicable it is. No. I do know a couple of things. My research area is not related to hardware implementation, so I am not 100% confident here, but I do know about a couple of results. So there are a couple of countries that are trying to implement quantum internet, which is kind of based on communicating with qubits, and they usually use BB84, if I am correct again. And I do know, so I am based in the UK, that they have a project where they have a communication in about 100 to 200 kilometers. And I would assume that they also use BB84 there. So yes, I will say it is probably approaching already where they are using this. In laboratories, I am absolutely 100% sure that they have implemented this. In real world, I believe there are some banks that might be starting to deploy these protocols, but again, do not quote me on this. But yeah, very interesting topic. Yeah.
Okay, thank you very much.
Of course. Anyone else? Some questions? I'm looking at the book that this course is based on. There was one extra bit that I actually thought was not that interesting or not really related to what you should be or what you will need to know. Yeah, I don't think this is important for you. It is about that if a box satisfies this equation we have seen at the end, so if it satisfies either of these two equations, that implies that the box is an isometry. Isometry being that if you do the transpose or the adjoint, then it cancels itself out. But this is only one way. But this is not that interesting and I don't think this is going to be helping you. The important bit is, first of all, the way to think about measurements. This Sterngerlach is a good way to think about measurements. So, you know, if you want to measure your particle, your quantum information, you have to kind of interfere with it to obtain some kind of result. And you can do it in multiple ways. And then we have seen that because of this, we can do BB84. And then the other thing to remember is that you cannot achieve a quantum copy because of the equations we have gone through. Okay. Again, any questions? I'm going to wait a couple of more minutes. Yeah.
So, is there no cloning? Is it, they call it no cloning theorem? Is it that the same thing as the no quantum copy, right? That is what you are trying to see as a...
Yes. No cloning theorem. I believe this is how scientists usually refer to this, but in this course we often kind of have a different terminology. But yes, you can call it anyway. So no quantum copy can be satisfied, or no cloning, no quantum cloning theorem. Yeah. If you know kind of the concept it represents, so then you can explain what it means, no cloning. Oh yeah, my R is very weird, and then I always forget to change it when people see it. No cloning theorem. All right. I'm going to stay here for the remaining 7 minutes. I think this is probably a good opportunity for those of you who have anything that you might not be sure about. You can ask me. But to those of you who would like to finish this call, feel free to leave. Thank you for your attention. What material will suggest for future study? So what material will you suggest exactly? Right, because I can't remember exactly I'm halfway through. So, oh, I see. So this is lecture number 5. There will be 8 lectures. So you're kind of halfway through. So once you guys go through this course, I would suggest there are a couple of options. So if you liked this diagrammatic reasoning, then Bob and Alex Kissinger, so Bob Cook is one of the, I think Bob will be there with you at some point. So he has another book. It's called I can't remember. It's the Dodo book. That's how we refer to it. It has a big dodo on it. A dodo word. It's PQP, picturing quantum processes, something like this. But if you search for Bob Kuke, and then you search for books that he wrote, then you will find the only other book that's not quantum in pictures. So that's a great book to read. So that's the book that we go through at Oxford. That's quite a heavy book, 800 pages. But I believe it builds it up really well. But the problem with that for you is that it's really similar to the content that you have seen in this course. So some of the things may look quite a bit boring. So in that sense, I'm not sure how much you would be enjoying it. But absolutely, I really like it because that goes properly into the terminology that people are using, and it explains more than just maybe what you are seeing. But it's a big commitment. It's actually a quite complicated question because I did it via that book and it was very good. Afterwards, there is an, yes, I actually do know. So Alex Kissinger, the co-author with Bob on the book I have been talking about, and John van de Wettering, another assistant professor at in the Netherlands. So they are in the process of writing a book right now on the ZX calculus. And again, this is a very hefty book. I believe it's 400 or 500 pages. It's more like a course. It has questions, answers to those theorems, really well built up. They are working on it right now, so it's still in development. But if you search for ZX book and then GitHub, ZX book GitHub, yes, then you will see a link. I might as well just link it for you. So then you will find this where they are kind of updating. And if you read the README, there is this PDF version that you can download. And well, I believe this is, in my opinion, this is a pretty good book. So it's really well built up. It's going to teach you kind of the bleeding edge of ZX research, going to give you a lot of concepts to know about in quantum computing, measurement-based quantum computing, error correction. That I believe that's a great book, yeah. And then in the meantime, I found the name of the book that I was referring to from Bob. I'm also going to link it. It's Picturing Quantum Processes. So I was correct at some point. Yes, with the pictodo on it. All right. I think I have exhausted this topic. Any other question? Okay, I am glad to help here.
Please, I still have some questions.
Okay.
When you were talking about the quantum key distribution.
Okay.
So we were talking about the sender, like the ALICE send the information to Bob, right?
Yes.
And first of all, you encode the information into a qubit, right?
Sorry, can you repeat the last? You encode?
You were saying ALICE will encode the information into a qubit.
In one qubit, it's a single qubit.
Yeah. And I was confused at some point. You see, you were saying there are two possible bases for him to encode it. Like there's the Z basis and then the which basis was that again?
X basis, yes.
And the X basis. And I was like, so how about the receiver? How is he going to choose his basis? Mm-hmm. What if they choose different bases? Maybe the one chooses the basis. How would that affect that?
Yes, that's a very good question actually. So this was about this was this slide, but yes. So let's say that Alice encoded in this green basis, which is the Z basis. Doesn't matter. Green basis is pretty easy to say, and Bob encoded in the red basis. So this is how it looks like, right? Yes. And then your question was, how does Bob know that actually these legs are not there anymore, right? Because Bob is just receiving some kind of random information. And the key here is that once Alice and Bob does these steps here, this doesn't look right, but once Alice and Bob is done with these steps, the key is that Alice and Bob broadcast their basis choices. So in this case, let's suppose that Alice chose, please, can anyone forward the link of the books in the WhatsApp platform? Yes, okay. So let's say that Alice chose, these are chosen uniformly at random: X, Z, 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 X, whatever. And Bob chose X, X, Z, X, Z. So in this case, they both have broadcasted all of these choices of bases, and they compare it, and then they see that the first choice of bases was the same, the third one was the same, everything else was different. And then what they do is very simply, they just kind of discard whatever they had about the bases where they had a different choices. And then all they are considering is the case where their choice of basis was the same. And then they look at the bits that they have sent. Does that make sense?
So when you say broadcast, you are meaning measure or?
No. Broadcast, I mean it in a, oh yeah, that's in a classical sense. So what ELAIS does is they have access to some classical computer, and Bob has access to some quantum computer, classical computer, and they kind of just share this information with everyone on the internet. So this would be this list of
Okay,
basis choices. Yeah. It's related to broadcasting, right? So this is a term I believe they use in cryptography, and that's why I might have been using it. Because you know how broadcasting works is they have these towers that kind of emit these radio waves, and this is called broadcasting, right? And then if someone is at home sitting with a TV, then they receive this information just like everyone else does, right? So it's kind of everyone has access to this information. Yeah.
thank you.
Any other questions? I'm really happy to help you guys with anything. Oh, sorry, Evans, I heard something.
Yeah. Please, I wanted to know if
I'm sorry.
If it uses
so either on my side or your side, the internet connection is a bit weak. So I'm not sure what you were saying. Could you repeat it, or could you write it down?
Okay, let me write it.
Oh, now it's good. Now it was actually good. Sorry. Okay. In the meantime, if anyone else has questions, just feel free to. Oh, Evans?
Okay, so yeah, I was saying that is this systems, do they use the continuous variable systems?
Very good question. So this is a bit beyond the scope of this course. So I can just briefly mention. So let's put this away.
Oh, no quantum copy.
No. I'm just trying to make some space so I can draw for you. But actually, I can just probably do something like this. Let's do this. So to those of you who are interested, there are kind of there are a couple of ways to think about quantum computing, and the one that you will see nowadays or through this course is that the quantum bit is this bulk. Like you can think about a quantum bit as a bulk sphere, so it's kind of a three-dimensional but normalized thing. And this is a qubit, right? Because it's kind of in the superposition of 0 and ket1. So this is discretized, right? Because you are there with 0 and 1, but at the same time, your basis, when it is an arbitrary quantum information, it's kind of somewhere in between the 0 and 1. But then this is just a qubit. What you could also have is photons, for example. So this is a Q mode, and you can kind of shine a light into this. And that's a continuous variable system. Why? Because the way you describe these properties of light are done through a continuous variable scale. So you describe its momentum and its position, if I am correct. You could also similarly just have like an infinite number of photons in each of these Q modes. We are not going to be talking about these things. I will say that when you are doing BB48, what you would be typically doing is you would be trying to use the existing optical fiber architecture that exists already in the infrastructure that already exists in the country. And then you would be shining some kind of light with some kind of quantum state through it. And that's so in practice, communication is usually done through light, which is a continuous variable system. But then what you do is you kind of encode quantum information, like a qubit, into the state of the light. And in that sense, you don't really need to care about it. Does that make sense?
Yes, it makes sense. But like you were saying, I was wondering how the measurement will be done if it is the whole process does not go through a Gaussian.
So measurements with so again, I am going to say that I am not an expert in this topic, but I do have a brief understanding. So there are kind of two ways I know you could measure a photon. So I did say that this Gaussian, well, I'm very bad at drawing these. So this Gaussian thing, Gaussian distribution, this is the way it is described is in the momentum and position. And then what you can do are called homodyne and heterodyne measurements. My understanding of these is that you, in a sense, kind of try to infinitely squeeze on of one of the axes, and then you measure in the other one. Another thing you can do, because this is kind of equivalent to describing the number of photons in each of the modes, is you could have these, once you have described your set of quantum operations on these Q modes, these are called. Then you can do some measurements that I will just lazily show as this, and then you get some numbers 1, 3, 1. This would be a photon count, photon number resolving.
Yeah, photon counting. Yeah.
Yeah. So in this case, that's what you get, the photon numbers.
Okay. Yeah. So I understand this. So this system does not deploy the continuous variable systems. I mean, what you are the whole concept about because I joined the class a bit late, and then I wanted to know if the whole system goes through the continuous variable system.
So these two are different concepts. The interesting thing is that my understanding, again, may not be right, but that many times people use photons not to do computation with continuous variables because they are not that broadly applicable as qubits are. So what they try to do is they use qubit, these continuous variable systems to encode a qubit. And this is what we are talking about. So this qubit is an abstract information, and you can create qubits using different systems, including continuous variable systems or neural atoms or ion traps, superconducting. Yeah, that's.
And some of the continuous variable, when you do the encoding, it's using the
Sorry, could you repeat what you said after the using the? Sorry.
Putting your input.
Could you repeat it again? Sorry, the internet is a bit weak somewhere. Yeah.
Oh, I was saying encode.
Encode D?
Encode.
Encode, yeah. So
yeah, encode. Yeah.
Encode. So your question is like, how would you do the encoding of these continuous? Like, how would you encode a qubit?
say it's a continuous variable system way. The system calculations to convert it to bit systems so that the measurements could be done.
Sorry, that I am really, I would really like to answer, but I didn't hear most of the questions because of this, the internet. Yeah.
Yes, it keeps breaking. I think you should type the question. That will be better.
Okay, yeah.
Okay, so I'll type.
Okay, but it's actually funny because now it was fine. But yeah, you can text it.
Yes, so
Yeah.
probably I'll reframe it well and then email it to you so that probably.
Oh yeah, I will type in my email address and feel free to ask me
Okay.
anything. Okay. So we are a bit over time, but I'm very glad that you guys are so eager to know more. Any other question? Well, in that case, I again would like to thank you for coming, and yeah, very good. Like I did enjoy this.
Okay. Thank you, Boldizsár, for this honoring our invite. And I mean, it's been a lively session, interact with him later on. Thank you again for honoring our invitation. And
Thank you.
I think the next session will be Friday. And also next week, we will have some presentations on the mini project that has been given. Thank you very much. So see you on Friday.